So the dot product. So first we'll go over some concepts and formulas. Now we have the two vectors with 3 components each. The dot product of the two of these vectors will be u1 v1 plus u2 v2 plus u3 v3. Simple as that. And technically the dot product is two vectors with an angle between them. And it's one way of expressing that. Angle is the inverse cosine of this expression. We have the two magnitudes of the vectors individually and plus the dot product on top. Now this can be equivalently written as this, and but yeah, it can be written this way, and even another way. You could have technically u times v equals uv times cosine zeta. And these would be vectors. I forgot to draw the arrows here, but you know by now. But yeah, basically some properties that orthogonal vectors have zeta equals pi halves and u dot v equals 0. And you can check by the formula because cosine of pi halves will equal 0. So this whole thing equals 0, so u dot v equals 0. Not too big, but not as significant as, zeta equals 0, zeta equals pi, have parallel vectors. The angle, the angle between u and v in formula. Yeah. Vector projection is just a formula here. It's u onto v, it's this form. If it's v onto u, it would be slightly different. Here you basically have to replace v with u and this and that. So that's basically if it was u, it was projection of v onto u. We just have to know this formula, and that formula you have to know them whenever it comes up. Which is not the most common thing. Mostly like you won't see it as often as other things. Like the dot product in general is the most important thing. Understanding this like number one property. But that's the scalar component of u in the direction of v. Remember, vector projection is a vector, scalar component is a scalar. And this is u in the direction of v, u dot v. Yeah. You can write it this way or that way, the same thing though in the end. So for the following examples, we find all this information. This was given as one of the formulas I showed earlier, scalar component vector. Basically, so the first one is just the dot product, and then of course we're doing this for two different examples with basically two different vectors. So if we have v and u have these components to them, the first part will have v dot u equals 2 times negative 2 plus negative 4 times 4 plus square root of 5 times negative square root of 5, because it's the components. You have the x components as x components. You could say y components y and z was z. Multiply them together. And of course, you add them up and you get negative 25, which, yeah, you can tell there's not a direction to it. It's a scalar. These are just magnitudes, by this point. I just show it out. You end up with 5 and 5 for both of them. Consequence of this will be same with cosine of the angle being negative 1. Basically just plug in negative 25 here and 5 for the magnitudes. Negative 25 is the dot product. And you get negative 1. Use the formula. Formula again, this one u dot, the basically direction of v. The vector v is what this is, and then that's how you do it. And u is plugged in the vector u. And this is a scalar. At the end of the day, it's the scalar projection, the scalar component of u in the direction of v. Similar. Yeah, you basically just divided out 5 in this. And in the end, you can get negative 5. Because you multiply them like a dot product, and then these two things get dot product. So the projection here is what's given, so we want to find, basically follow the formula. That's what you do. You follow the formula. So in a formula problem we have to note, because you basically take the square of the magnitude of the vector v and u dot v here, top, and you have just a vector v. And you get a vector in the end. That's why it's projection, vector projection. And now here's another problem. Here's vector v and hex vector u. K is not really, j and k, but I is like 0 basically in this one for u, which is seen with this one. 10 times 0, yeah, because I is basically the component will be 0 when it's not existing. Then you do the same thing. 25 is what the dot product is. You see component by component, 11 and 3, negative 2 and 4. No, just the sum of the component multiplication. 25. And magnitudes are calculated like normal. The cosine of the angle between u and v will be 1/3, calculated using these various things. Because remember, technically u dot v is the same as v dot u as far as dot product works. So calculate v dot u, but it's also u dot v. And C and D are where they matter, that you pay attention to how it's asked, like projection VU, like this. You could have UV and a change, as I said before. But C, you follow the formula again. Vector U times the direction here. Dot product between these two different vectors, and you get it. In the end, you get 5 surds. I can't really explain it. I can just show you mostly the mass here. And then projection yet again, u dot v over the magnitude of v squared, dot the product v, or times it, not dot, times it. Because this is just going to be a scalar, and that's going to be the vector, and therefore you get a vector and then scalar here. This is technically just a scalar, because that's a scalar, that's a scalar, scalar is a scalar, and it's multiplied by a vector, so the end product is a vector still. You can't get these, you just have to be very careful. Follow the formulas. So if we have these, now we have 2 more vectors, just one more time, the same process, a, b, and c, d. I plus j plus k and 5j minus 3k. So a relatively simple vector for u though this time. And as you can tell, 0 times 1 plus 5 times 1 plus negative 3 times 1, because it's all 1 for this on the components, and 0, 5, negative 3, because 0 times I would be 0 basically. That's why it doesn't show up in V. But 0 plus 5 minus 3 equals 2. Magnitude is same thing. We could technically show 0 squared plus 5 squared plus negative 3 squared, but 0 squared is 0, and anything added to 0 is going to be the same change. So square root of 34 and square root of 3 are magnitudes here, obviously. Cosine theta formula again. It's 2 divided by square root of 3 times square root of 34. And I decided just to do 2 over square root of 102. Just might as well keep it 1 square root on the bottom. But that's just 3 times 34 equals 102. That's why I did that. Let's see, go back to how it started basically for this, but this is the scalar thing. Trying to get a projective, but same type of problem. It's like u is I plus j plus k. You have 5j minus 3k divided by square root of 34, because that's square root of 34 is here, v, and then 5j minus 3k is just v itself. And vector u, vector v, magnitude of v. So and then we multiply them together. We basically, there's technically a 0 is 1 times 0 in here, but I admit that, like I said, because that'll not change the answer. Adding 0 does not change it. But yeah, doesn't this one, basically just adding, you're just basically adding these two quantities at the end. So, and it ends up with 5 minus 3 over the same denominator, which is equal to 2 over the square root of 34. And finally, the projection part, like the other two problems were like. And you go through the formula, you have 2 from before the dot product, the magnitude of its square, square root of 34 squared is 34, and the vector v, 5j minus 3k. And that gets to 2 over 34 times that vector. You can simplify it down to 1/17 times it, and you have 5/17 j minus 3/17 k. So this question for two other questions, there's a fact that you can asking to find the angle between two vectors in each example. We want to do it to the nearest hundredths radian in this case. Radian. Yeah. So 2i plus j and I plus 2j minus k. But basically I make a point here first that you need to know this formula, one of the formulas involved in this relationship between them, and you're good. Because we know from pre-calculus that the inverse cosine of cosine theta will equal theta, and of course you just take the cosine inverse of this side. Point is that cosine theta equals the dot product of two vectors divided by the individual magnitudes, multiplied against each other. Basically, and then you can just say the inverse cosine of this on both sides will give you theta equals inverse cosine of this expression. Here's the example, is this first one. U dot v is simply 4, because it's 2 times 1 plus 1 times 2. 2 times 1 plus 2 plus 1 times 2 plus 0 times negative 1. And it's equal to 2 plus 2 plus 0 equals 4. Sure. And u is, of course, again the square root of the square of the components together. Square root of 5, because it's 2 and 1 for u. 1, 2, and negative 1 squared each of them will give you 1 plus 4 plus 1 equals square root of 6. And in the end, it's inverse cosine of this expression, which you put in a calculator and make sure your mode is set to radian. You set it to not degree, but to radian, radian. Ugh, can't say it today. Yeah, 0.75 radians is what you get. You just round. I put an estimation sign for these as well for that, just to make it clear you're only rounding here. You get these two vectors, which they have square roots in them, but that does not change the fact that at this point in your math career, you should have, at the Calculus 3 level, or any multivariable calculus course, have a basic feel for this kind of stuff. So simply put, u dot v will give you negative 4 in the end, like before, and the magnitudes are the same as before. And in the end, you do negative 4 divided by 2 square root of 13 times 2 square root of 2. I mean, yeah, you could plug it all into the calculator. You could also do this, but you just simplify it down and just enter negative 1 divided by square root of 26, and then do the inverse cosine of that, because I was simplifying it. But you get, regardless, you should get 1.77 radians here. Okay, so for one last type of example using dot product, we have the triangle. So we want to find the measures of the angles of the triangle whose vertices are a equals negative 1, 0, b equals 2, 1, and c equals 1, negative 2. And I even crude sketch, but the only point of this is to show how the angles work. Basically, the idea is that the vectors, two of the vectors from the same point, and the angle, you can use that to determine the angle, basically. You have these two vectors, and you do that for each one, so we have technically 6 different vectors, technically. Yeah, we do have 6 different vectors, even though 3 of them can be found somewhat simply. Well, all of these are, because it's only 2 points for each of the points. I mean, 2 coordinates for each point, would be the proper way of saying that. So, like in unit in the last section, basically you do these old way of like just, you subtract the end point from the beginning point. So 2 minus, but AB, it's B minus A's components basically. So 2 minus negative 1 is 2 plus 1. That's I, since it's x. The y coordinates 1 minus 0, which is j, of course. Here for the y array, so 3i plus a, and this is continued for all these. One of the things to note, though, is that you could technically just take the negative sign of the, basically apply negative 1, the scalar negative 1 to both, to the whole thing, and that'll give you BA is negative AB. As you can see, negative 3i minus j, 3i plus j, they're just negative inverse of each other. So that's one way you could speed it up a little bit, the process of taking these vectors. And so we're going to use this formula down here at the end. It's the theta equals cosine negative 1, A inverse, theta, the angle equals the theta, which is also called the angle, equals the inverse cosine of the dot product divided by the two magnitudes of each other. That's the point. You basically have to do that for each of these, which seems annoying in the end, but at least it's relatively simple. It's just, yeah. And I show the work here for all them, the magnitudes. The only good thing about magnitudes is that BC and CB's magnitudes will be the same, and same with CA and AC and AB and BA, because they're just negatives of each other, so they're the same components, just negative. So square of a negative is the same as the square of a positive number. If they're the same, the absolute value is the same, the square will be the same. So that's the trick, and you eventually get first angle for A, angle at A, which is 63.435 degrees. And then here, angle at B, you plug in those values from all this work, from this work particular. Again, you get 53.130 degrees and then 63.435 degrees for the angle at C. And this is a little, if you remember from geometry, all three angles of a triangle should equal 180 degrees because a triangle has a total of 180 degrees internal angles. And it's a isosceles because it has two equal angles. That's not necessary for this problem. It doesn't ask about that. It's just, I set the note. Yeah, you have those three angles.